Okay, because the first few slides, 30 slides, will be about the introduction to the course. So I think we should get over it quickly, because there will be another like hundreds or so for the review, which will review lots of mathematical concepts that you will have to encounter throughout the course. Okay, there will be the reviews of concepts that I suppose that you have already know, which many of these are concepts related to linear algebra and how to write Python program related to linear algebra. Okay, so in any case, let's get started. Right. Welcome to Deep Learning course. For this year 2021, we are still learning it online like this. So I expect that some of you that most of you that are here are interested in the application of deep learning as well as the insight of the deep learning models. What you encounter in this course will not be about how to write a program. It will not be about the special latest technique, but we will instead focus on the foundation of deep learning. We will look at how deep learning are formulated, and then we will further extend our knowledge toward some of a more advanced architecture and see how are those architecture has been described by the mathematical concepts. Understanding mathematical concepts are important if you want to be able to excel in the deep learning area. So I suppose that you are in this course because of that. Otherwise, I guarantee that it will be a bit suffering because you encounter lots of mathematical formula and the derivation of the mathematical formulas and extension to the application, to writing a program a bit. So it will be like combination between both. We will also have assignments, which they are all coding assignments that you have to write. Some of them you have to write the program from scratch, write the learning application from scratch. Some of them you can use the library to do so. Okay, so let's start. You have I would say in the modern era, now today, that's a word that you usually use in the report, right? So we have seen that artificial intelligence, AI, has been part of us, has been part of our life, right? And we all see that they have certain intelligence in them. How are they created? Right? What are they composed of? Those will be the questions that we will pursue in the more foundation perspective here. Okay, AI is described as an area of study, as you may have known, that focus on mimicking human behavior, mimicking human intelligence. So we are creating a machine that should behave, that have certain cognitive intelligence like human. Sometimes AI is also known as, in a larger field, the cognitive computing, right, which may encapsulate not just in AI alone, but also other related topics like language, learning, planning, optimization, problem solving, and other things. Right. When we talk about AI, there are a certain tasks that we know we expect them to perform. For example, in an AI, you might expect an AI to be able to match the pattern with certain output, match certain input with the output, and then we want them to learn the patterns from the historical data. We know those as we call the techniques like that as the machine learning technique. Right? Inside machine learning technique, there are like numbers of number of methods that you can learn, like decision tree, random forest, gradient boosting, or even toward deep learning and families of the deep learning technique. Okay, in the field of AI, there are application-wise in AI as well. Like when we talk about speech application, when we create a machine that can generate a human speech or can perceive human speech, right? Those are the speech processing tasks, or the machine that can evolve its speech pattern. That can mimic human, right? And on the other hand, you have an applications that can interpret image, perform tasks like human in something like human vision. These are the fields of computer vision, machine visions. There are classes about this as well. If you are interested in those, you can take those classes and you encounter models and techniques that will be different from just deep learning alone. Deep learning doesn't solve all the things, right? Although it is quite I would say the novel approach in research in a lot of applications. Deep learning doesn't reveal the insight of the process. It doesn't reveal which features are important. It doesn't reveal which mechanisms and how it works. So if you want to create a model, to perform simulation, perform something that close to human, deep learning might not be the things for you. Right? You might want to look at the model-based learning. You may want to look at other things. Okay, natural language processing. This focuses on how can we process natural language. How can we generate natural language? Right now, the field of natural language processing and the text processing is occupied by the deep learning technique. Although we go back like 20 years ago, most of the technique are heuristic technique and some of the machine learning technique as well. And there are also other fields in artificial intelligence like expert system, optimization, and robotics. Okay. Therefore, artificial intelligence is like a superset of the technique. And when we talk about machine learning, it is actually the subset of the AI. And deep learning is even a smaller subset of the technique. But even though it is quite a focused area, it can be applied in many fields because its power in learning the association between patterns. Okay, so how do we define the deep learning? Let us first define machine learning. What is machine learning? Right? Machine learning is like a technique that you allow the machine to learn the pattern. Right? You allow the machine to learn how to associate between features and then do certain tasks like distinguish between class, like what you see here, or perform estimation like in regression, divide the data into groups, or do these things like tagging whether the email is spam or not, identify which search you would like to see, or perform the chatting, perform conversational control like in the chatbot. Now, if we were to define deep learning mathematically, deep learning is a way that we want to find the function, or sometimes we call it a model. Like a model that when we give the feature, the set of feature X to the model, this feature X would pass through the function fx, and we got y here. Usually, in the machine learning task, we would already have the x and y collected from in forms of data, and then what we are trying to do is to estimate this fx by different methods. Like when we use decision tree, we try to infer that this fx should be partitioning based, like the model that based on partitioning, the discrete partitioning of data. When we use regression, we are trying to explain the association between x and y as linear combination. That means x has to somehow linearly correlated with y. When we use other technique like random forest and gradient boosting, we are trying to infer that there are certain quite complicated subset and association that in forms of partitioning as well between x and y. And also different method would base on different assumptions. For example, suppose your data x is a sequential data and y is a class. Fx should be something that is suitable for this type of data to explain the process. If you use decision tree to map between them, can you do that? Yes, but fx might not represent the actual process. But if you were to use something like hidden Markov model, conditional random field, or the RNN, then association between x and y will be more proper. Right? The task that is to identify the model that are suitable for this type of things is belonging to the, well, modeler. I usually call myself a modeler, although I'm not associated with any type of modelings in the modeling sense, you know that, right? But well, nowadays we have different names like data scientist, AI engineer, whatever. I'm still calling myself a modeler. I like to create a model. Although my model is the mathematical models that kind of finding associations between things that you see. Okay, so when we talk about model, right, model is a set, is a like a defined formula, a defined structure that you that have a certain set of parameters. Those set of parameters will explain the association between the data that you have. In the model, when you want it to be learned, that you need to have a certain something that is called cost function or objective function or the error function. Well, the same thing, or the loss function. Then you can use these as a criteria to optimize the parameters. Okay, so this is like the basic concept here. We will talk about it in more detail in the lecture of machine learning, which we will learn about the machine learning concept mathematically. The form of learning can be different depending on the task, depending on the situation that you have. Supervised learning or unsupervised learning or reinforcement learning. In the supervised learning, we have input and output pair. What we are trying to what we are trying to do is to associate input and output together. Sometimes output might be the thing in the future, and that we are creating a predictive model. But sometimes output can be the thing that is now, and what we are trying to do is to create a system that can interpret the data, like seeing the image and deciding what to do. Okay, so something like this, given the robot sensor camera input, you want the algorithm to kind of find the movement that it should do. Okay, so that's not the future, that's something that it has to do. Or creating a search engine that when you query the search terms, then it identifies maybe products that are close to what you are searching for. Right, so here you need to teach the system input and output. Okay, have input and have output, and then trying to associating them together. These are supervised learning. The tasks of supervised learning, like classification tasks, localization tasks, object detection, and segmentation. Although some of these are like combination between, I would say the combination between supervised and unsupervised, that trying to like minimize the region. But let's put it this way, like classification is supervised learning in this case. Okay, so for the supervised learning, what do you need to perform the task? You need to have a lot of label, manually label data. This is important. You need to have the manually label data, or the data that are labeled not based on certain criteria that you want to use them as input, but based on other things. It might be based on criteria, but those should be the criteria that you are not including in your X. Otherwise, you will generate, and sometimes you call this overfitting, but I usually like to call it in more philosophical term. You are creating a circular reasoning. You are putting the output to reason as the input to produce the output, and that is circular reasoning. And circular reasoning is not acceptable. In reasoning, you should not use your end goal as your assumptions, right? So that's the philosophy related to model. Okay, so when you are building the supervised learning, you need to have certain thing that you aim to predict. Those are the target. And identifying a target is actually very essential to solve proper business problem. If done right, then we will have a simple model that is powerful. If you perform it wrongly, then you have a model that you cannot use in any case, right? For example, you might want the task like churn prediction, online game churn prediction. You might want to predict which user will churn or not returning to the games based on the playing pattern. In that case, you have the label as churn and not churn, active and not active, and then you have the previous historical data of those users playing the game in the session. In the credit risk scoring, this is also another example of supervised learning. You need the data comparing between those who have problems with credit, not paying, and those who those who are okay, paying on time and whatsoever. Then you can train the model so that you have the model that is trained based on a certain. These are like the classic method in credit scoring. First, you need to identify the variable based on the weight of evidence. Once you get the set of variable, you can train the model, and then you can predict using the score. And you can use the test set to validate whether the result is okay or not. These are the tasks of supervised learning. The unsupervised learning relies on similarities, co-occurrence. Something that say they are close together. Okay, so the unsupervised learning technique allows the model to identify patterns. Those patterns are something like the consistency pattern in the data. So it will find some structure out of the data set, like in clustering technique, which will find the cluster of data that are close together. In the graph clustering, it might find the graph cluster that have certain associations between them. Okay, unsupervised learning is a quite attractive technique when you want to look at the arrangement, the structure, the outliers, the group of data that occurs together. Like in retail, you might want to see whether customer would buy the products, whether they would buy the product together in a set, and which product is usually bought alone. So understanding this would allow like the marketing people to come up with some strategy to sell the product. Examples are like the news story. Right? News comes out every day, right? In order to process the news, nowadays there are a model that can group the news together if they belong to the same category, like performing something like text clustering or topic modeling. Will allow us to identify that the news are close together and they should be grouped as same group. And if those group contain certain labels, then you can certainly propagate those labels to those that you do not know, that you do not know which topics they contain. This is an example of the study on Brexit. Oh, this is quite a long time ago, and I still use this. Like, oh man, maybe I should use something like COVID-19, right? That will be more of the latest. Never mind. So these are the topics that on the news article that are related to one another in COVID, using the technique called topics modeling and graph analytics together. And then you can identify that certain topics are associating with one another. And then you can see that there are certain isolated topics that have been discussed but are not linked to others. Okay. So these are the first is the supervised learning, unsupervised learning, and this is reinforcement learning. Reinforcement learning use simulation, right? Quite exciting. It uses the environment that you need to define. The environment contains the state, action, and reward. You need to define all of this so that the model that you train can learn from this environment. So it depends on the environment that you create. Which will allow you to train the model differently. For example, if you were to create a very realistic stock simulation, and you let the bot decide whether to buy, sell, hold, or doing the stock actions, then the bot can decide whether to take action or not, and then it will take the reward as the objective, and then let the bot learn what to do, and then afterward you can then use the bot that is learned based on the virtual environment to deploy in the real thing. So hopefully it would work. Let's take a look at some example here. This is an Atari games that use deep Q learning to learn the action, whether it should go left or right and how much. Yeah, let's take a look at this. Okay, so these are the first 10 minutes of learning, and you can see that the bot still cannot control very well, so it missed a lot, right? And once it missed, it will be like there will be penalties to the objective function. If it can receive that, it earns some score after 2 hours of training. Doesn't specify what type of computer it used. You can try it yourself using deep Q learning to write the game playing like this. Right. So that is reinforcement learning. Okay, and there are other types of technique, many models in machine learning. Some of you may have already encountered some of this, learned it with me in the other courses. Like there are technique on the ensemble-based models, on the Bayesian, on the technique to reduce the data, to compress it based on dimensionality reduction, and other types of techniques which will be suitable for different tasks. An example of the combination of deep learning and reinforcement learning is the AlphaGo. The AlphaGo has different types of network that perform differently. Some of them will be the policy network, which select the policy to perform. Some will be the value network that based on the value, based on the actual perceived value, and then choose the action. Then combining the result of all of these, the AlphaGo make decision on what type of thing that it should do based on certain Monte Carlo tree search. So there will be certain randomness in the movement. Okay. If you are interested in the AlphaGo, in the reinforcement learning and combination, or the combination of different type of network together, you can find the link in the credit here. But I would suggest that before that, you should understand the supervised how to create a deep learning model here first, and also how to do reinforcement learning. Then combination of them will come afterward. Right. So that lead to here, to the deep learning. Deep learning is one of the exciting technique, one of the exciting breakthrough in machine learning. It can learn structured. It can learn the goodness of deep learning. It's not in its capability in the tabular data, in the structured data. No. Structured data. If you have structured data, you better use general machine learning like decision tree, random forest, the gradient boosting. But when you have the unstructured data, those machine learning techniques would be struggles to beat deep learning techniques. Why is that? Because there is one essential thing that deep learning can do, which is to extract features automatically. Right? It can. That's why it is good for the unstructured data. It can learn the representation of data. Right? This technique can apply the knowledge that it is learned from one task to another task as well, and you will see that in the latter section, especially in the technique like embedding, in the technique that compress the data in autoencoder. We'll look at that later on. You also link multiple input at the same times. And it can also understand different types of unstructured data and the series data, and then can be used in complex environment if you train it properly. So if we were to build the deep learning and AI association, AI is like the general fields that contains lots of technique. Reasoning is also one of that, not related to deep learning or machine learning at all. But the logic, the logical operator, that is actually originally part of AI. Machine learning is like a subset of deep learning, and deep learning is part of the technique that learn the representation, right, inside here. Okay, what is representation learning? In the system, right, if you were to go outside and then look at, if you work for the company and then look at lots of systems in the company, you will see that right now, the state of AI in the company mostly relies on the hand-designed program, on the threshold, on the logic, on the if-else tree that has been decided. This is the rule-based system, right? This is one of the classic artificial intelligence that we are trying to incorporate the criteria into the system so that it can make decision based on those criteria. That the reason I call this an AI, because if you go back like 20 years ago, or 20 years ago, the field of AI actually encapsulate those type of things as well. When you want to make reasoning, judgment, decision, that is part of the AI. And if else is actually part of the AI, on the original AI, the expert systems. Move on to about the years 90s to 2000. The technique on machine learning has been advanced, partly because of the power of computer and also the algorithms itself. We have lots of technique that can map between input and output. Actually, my early studies were driven by these types of things as well. Back then, it is called pattern recognition. I have a book called Pattern Recognition back then, and then it is mostly used with like signal data, image data, to perform different tasks that is not quite commercialized yet. But now today, because of the general framework that anyone can use, so now we can apply the machine learning to data. And then part of the data science is a study by creating the model based on the phenomenon as well. So these are classical machine learning. Right? You need to have like hand-designed features, like extracting features of this month, comparing to the last month as a tabular data, and then let the model learn from those tabular data and then make decision later on. For the deep learning and the representational learning, you have input and output, but you want the model to learn all these things. It needs to learn the features and learn the mapping. And in the deep learning sense, it needs to learn the additional layer. You need to learn which layers are important, which are not, and then make sense and then trying to kind of prune them out themselves if possible. Okay, this is representation learning. So deep learning has been applied to different types of tasks. This is one of them. It can be used to perform image classification. In the ImageNet competition, the participant has to classify like 14 million image of to 20,000 categories, and these images are annotated manually by human, so we can be sure that they should be correct. And it has been tested on many sets, and some of the model is quite powerful that you can even deploy to on once it learns the image net, you can transfer it and use it on other tasks as well. So it looks like this. This is one of the this is a Google net, right? There are many different types of network, like the VGG, the REST net, which we will talk about it later in the convolutional neural network lecture. So you will understand why are they working and why the usual feed-forward are not working. Right? So it looks like this one. It contains lots of convolutional layer and other type of layer, which if you do not know right now, it's fine. We'll talk about it later. But yeah, it's called deep because it contains lots of layer, from input left hand side here to output here, right? That you have the softmax and fully connected to perform classification at the end. Okay, And the deep learning model has to be exposed to lots of input, and then once it is exposed, the weights in the model will be learned at different layers. Each of these layers can be extracted to view what happens there. And actually, when you learn further in the later lectures, we'll extract this feature map out to see what actually happens there and why does it matter. Okay. So we can use deep learning to perform machine perception. Actually, you can use this is like the image that tells you the story about the usual machine learning. In usual machine learning, you have image, you have to extract vision features, then perform the task. In the speech audio, you have speech audio, you have to extract audio features, and then perform the task. In text, you have to extract the textual features and then perform the task. But in deep learning, you are kind of including this feature extraction toward the model. So the model will have to do the task entirely. But that's not always true. For example, when you study about this further, you will see that sometimes pre-process the data before putting it to deep learning is a good way to do the job. For example, if you work on speech processing, putting the whole audio file into the model is not a good idea because usually the speech content is in form of frequency movement. So you might want to convert it into the spectrogram, convert it into the filter banks of the frequency. Or if your task is to image is quite obvious, so I'm not going to talk about it here. For the text, you need to process it somehow so that the data, like for example, you need to actually tokenize the text first, like for example, to do the Thai text processing, tokenize the text first before doing all the tasks that related to text analytics there. Okay, and deep learning can be applied to different work. You can see that it works for image. It also works for natural language processing. There are lots of work related to natural language, which I cannot cover it here in this course entirely. So usually I would have the text mining course separately, but this year I open it for the undergrad to dump it down to the coding level. But I think there is a course called natural language processing. If you are interested in the detail, you can register for that course. For this, I would just want to mention that you can use it with natural language, and we will briefly work on this in the language modeling and in the sequential data in the recurrent neural network later on. Okay, so learning the representation allows to identify the word that have similar context, like the word to vec, that train on the quite basic structure, but it can learn the association between words, or the machine translation, the attention, the transformer, the latest technique that allow you to perform the sequential model that capture the context in the sequence as well. Combining them together, right? You may have the model that learn from image and then generate the language by plugging in the structure, the convolutional structure with the recurrent structure. Let the model learn itself on how to translate from the picture into the sequence of data here, or from text to image. That when you describe it as text, you can generate image based on certain generative model like GAN, the generative adversarial network, which is quite an interesting concept that can be used to do the generation as well as to perform to be part of the analysis system to train the model. To use deep learning nowadays is not that hard. There are plenty of open source that you can use. These are not limited to. These are some examples, and they are quite like the leader in the fields. In my course, I usually use Keras and TensorFlow, which is quite simple to access. But feel free to use PyTorch and others, because our course will not be about coding. Yeah, yeah. Some of you have passed tests already in coding in AI. Our course will not be about coding entirely. Our course will be about the inside of the model. So it will be about the mathematical foundation of the models. Okay. So here are the learning outcomes. The learning outcome in this course is to understand the mathematical formulation of the deep learning neural network architecture. Deep neural network architecture, and you will also implement an algorithm in deep learning, but mostly you can use libraries later on, but I think first 2 lectures you need to write it your own, if I remember correctly. Never mind. And lastly, you have to do the research in deep learning as well, and then present the papers to the class as the term project. I usually not call it a term project. It's like actually a term paper. You have to select one paper, one interesting paper that you would like to study, and then present it to the class. And your score will depend on the intelligibility of your presentations and how well you teach your peers about those techniques. Here's the textbook, the reference book that I use. Quite a hardcore book. By Ian Goodfellow. Right. In this book, there are no codes, but there are actually lots of equations. Yeah, lots and lots of equations. So yeah, we will use this as the textbook in this course. If you want to read through this, I would, if you are a new beginner as a starter in deep learning, I will not recommend this book, okay? Because this book is very, very difficult. It contains quite a lot of mathematical concepts that you probably need to have certain backgrounds before we proceed further. But if you want to start in the foundation of deep learning, this is one of the book that you must have. The simpler one would be deep learning with Python. The simple deep learning with Python by the one that wrote Keras, or the tutorial online that you can find on the Keras and the TensorFlow and PyTorch website. Okay, and the topics that we will cover in this course include the introduction to deep learning is actually this one, actually it's from the last time, and this time we will cover the topics of the review of all of these theories, which quite a lot. So I'll move along with the topics quickly, although I think I spend lots of time here. No, it's still fine. I still have about 2 hours to cover. And the next time we will then jump to the gradient-based optimization, which you have the first assignment to write a program to do the gradient-based optimization. Then you learn the basic concept of machine learning. No, we are not learning about decision tree. We are going to learn about the basic of machine learning, about the loss function, the posterior probability, and authors, okay, and optimization as well. And then it will be about the deep-forward and backpropagation algorithm and optimization of the deep learning. We will learn about the Adam, Nadam, Nesterov criterion, the adaptive moments and others, and why does it matters and how does it work, mathematical terms, and in the library which already have this thing to input as parameters. And afterward, it will be the class about convolutional neural network, and then a simple image classification. If you already take coding in AI or other deep learning course, this will be like the first one that you work on, but it will be the 7th lecture. And what you forgot on is not actually in terms of implementation. Implementation itself is quite simple, but I want you to look at the detail on why does it work in the convolutional sense. Maybe you will create something that's similar to convolution later on. Okay, and then no class because of the midterm. After that, we will learn about regularization. One dropout is one of that, but you can create different type of regularization based on the structure. We'll look at that here. And then recurrent neural network. And the embedding, which is, and then we perform text classification here. Then there will be like 3 lectures, which I will cover the three advanced concept here. Last year I covered the Siamese network, that's why it's here. And for this year we'll talk about the self-attention here to learn about self-attention a bit, and GAN to learn about GAN here in the advanced topics. Advanced topic can be changed, okay, if you want to learn about something else, but well, at least I'll cover this, and it can be reduced as well. hopefully not reduced. So yeah, so about these three, the advanced topic for this year. These are usually changed years by years. Last 2 years, these are not there. So in the past year, I covered something like autoencoder, and I don't remember. But because we can talk about autoencoder here as well in the text, in the embedding representation, so I kind of compress it a bit to cover something else for one-shot learning and self-attention and GAN. And then lastly, the last two slots here, you see that we have the research presentations, which you will present one paper to the class, okay? And each of you have about 20 minutes or half an hour to do the presentations and present the work to the class. The score for this class comprises of three parts. First is the assignment. In the assignment, you have to implement these five models. Although I said implements, in the implementation, you need to also solve the equations, because, for example, you want to perform gradient-based optimization. You need to solve the cost function, show the loss, the loss function, and then take derivative of the loss function to determine the gradient, and then perform gradient descent. So there will be both mathematical formulations and the task itself in these assignments. Okay, there will be 5 assignments, and in total it comprises of 40% of the score here. Another 40 come from final exam, and the last one is the research presentation. Okay, so this is all of the work in this course. Do you have any questions about it? First? Otherwise, we will take a short break and then come back with the review of the mathematical concepts required for the class. Any questions? During the class, you can chat in to ask questions. You can open the microphone to ask the questions. I don't mind. Both are fine. And we will start the class on 6 p.m. Except if I have like emergency, like last time, stuck in traffic, I came back like 7:30 something. So yeah, that's not practical for starting the class there. Right. So if there are no questions for now, let's take a break, and then we will start the review on 7 p.m. Okay, if you have questions before then, please put the questions into the chat box. Okay, let's take a break. เขาต้องไปทำอีกนู่นอ่ะเสร็จถึง3 ทุ่มอ่ะบอกแล้ววันนี้ยังไม่ได้มีแผนเยอะไม่ได้ลูกไม่ได้เพราะว่าตะวันอ่ะยังทำเจอร์นอลไม่เสร็จเลย
ไม่ใช่เหรอเพราะตอนทำ
ไม่ได้ตะวันยังทำไม่เสร็จมันทำไม่ทันตะวันต้องมาทำเจอร์นอล
เมื่อกี้เพราะอินทรัพตอนเมื่อกี้ตอนกำลังจะบอกว่าตอนทำไปแล้วได้หลายนัก
มันต้องมีกี่หน้าตอนนี้มีกี่หน้า
หลายมากไม่ใช่แถว20 เกิน
แล้วตอนทำได้4 หน้า
อ่านอันนี้คือ chapters
เนมแล้วก็
chapter 2 what is online learning online learning is when you learn on from home using electronic or you might think you're in a classroom at school but instead of going to school you will learn on online on computer apps called Google Meet, Zoom, Microsoft Meet
ใช่เหลืออีก8 หน้าเนี่ยต้องทำให้เสร็จ
มีเต็มไปหมดเลยค่ะอ่านฝึก
เกมยังไม่ได้ทำไงให้เสร็จก่อน
ให้หมดเลยเหรอ
Right, welcome back. We are then going to proceed with the review of the mathematical concepts you require for this course. Okay, so hope you are already here. Right, so what we will learn later afterward would be about linear algebra, probability theory, and the information theory related to the course. You can follow the code here, but I'm not going to particularly type them here, so you can review the coding later on. I put it here in the slide as well if you want to like practice afterward to see what types of features that that Python has toward addressing different types of problems here. Okay, let's start with scalar. Okay, scalar value. When we talk about scalar value, we are referring to just a single number. Okay, usually in the course and in a lot of book, we usually use the lowercase variable to denote the name of the variable or the value related to the scalar values. When we refer to scalar value, we usually define it as a certain types of value, like it will be the real value or the natural number, right, depending on the set that it belongs to. Okay, once you combine the scalar value together in form of the structure, you have vector and matrix. Right? Matrix is a set of elements that you organize them into row and column. Right? Usually it is written as this: A equal Aij in the square bracket. This belongs to the R m times n, which means that you have m row n column. Okay, m row n column. That's why we have indexes like this. Okay, we call the matrix an order. We call an element of the matrix an orders of the matrix if it refers to the number of row and columns of the matrix. Right, we have the order of matrix 3 times 4, which are the row times columns. Right, 3 row, 4 columns. Right, order of matrix used in referring to the data, the shape of the data. When you create a model, you have to be sure that the shapes are right. Right, you use .shape in Python. It is related to the order of the matrix. A square matrix is a matrix that have the same value in both dimension, in both row and column. We usually use square matrix in different places, like in graph representation, in the principal component analysis, in the matrix inversion, in the pseudo inverse case. Okay, the diagonal matrix arises when you combine the values, something like an eigenvalues, or extract the eigenvalue from the characteristic equations, and then you encounter the diagonal matrix. They are the matrix that have like the values in the diagonal line. Sometimes you have a matrix that contains value just parts of them, like in the upper triangular matrix, you have the matrix that have values only in the upper part, or the lower part here called the lower triangular matrix. These matrices are usually used in representing distance matrix. Come from calculating the difference or the similarities between data. Scalar matrix is a matrix that have that is like combination of diagonal matrix times scalar values. You get the scalar matrix. It is usually used to represent like a scale value in the matrix form. Okay, identity matrix is a matrix I that have certain specific criteria that you multiply it with anything. It results with the square matrix. It results in the same matrix. So it is behave like value of 1. Right. So identity matrix has the value of 1 in the diagonal line and 0 elsewhere. You can create matrix in Python and then play with them, like using NumPy, using arange. You can create a vector. One time number of dimension that you want to generate. And if you create a two-dimensional matrix, here something like this, you can create a list np.array. You have the matrix in 2 dimensions, and you can use a special type of function in NumPy like zeros to create a 0 matrix, 1 to create 1 matrix, and np to identity to create identity matrix. NumPy also has the function that you can multiply matrix together, like np.matmul and np.dot. This allows you to multiply the matrix, the two-dimensional matrix together. So if you have the matrix B, you can multiply it with I that we generated earlier, and then get the results as the same matrix. So I times B equal B and B times I equal B. Okay. When we have a matrix in one dimension, particularly in the column dimension, we usually call this a column matrix. A column matrix has been found in lots of applications, because when you represent the y values as sometimes we call them a column vector, as the set of value, then it might be arranged as a column vector, and this column vector would represent like certain value that you want to associate with. And in a lot of technique, a column vector also represents different things. Like when we will see later on in SVD, in the singular value decomposition, or in principal component analysis, the column matrix or column vector can be extracted out to get the eigenvectors of the reduction process. Okay, used in general data science concept here, the column vector. Now it comes to the vector. Right? When we talk about vector, what is it? Scalar is just one value. Matrix, you have two dimensions. Vector is actually a matrix, an array of number. Right? Just that is arranged here. Think of it as a column vector. Right? It is arranged in order. The orders are important. You can identify it by index. Usually in mathematical term, you would write it as a lowercase bold letters, bold lowercase letter to denote the vector. Okay. So elements in the vector will be denoted as a subscription here, like this is x1 and x2 and so on, like this. What is actually a vector? A vector or the column vector can be thought of as in the geometric representation terms, it can be thought of as an arrow here like this, that point starting from the origin to the point of the value that you want to represent. This is the two-dimension the vector in 2D that representing the direction or actually the direction and size from origin to the point of interest. Okay. When you have vector like in 2D like this, you can write it as like the two elements vector like this one. These two are also two elements like V and W like this. For the vector in R3 in the 3-dimension, right? This is also just a column matrix, just a column vector. This is 3 times 1 vector with 3 elements like 2, 3, 5. It is the vector would point starting from origin to the point 2, 3, 5. Or you can think of it differently. You can start from 1, 1, 1 and then point to 3, 4, 6. And it is still the same vector. But that is like high school math, and I'm not going to go in that part. So at least here, yeah, the vector in R3 can be represented as like a set of value, like 3 values that you've written all together. Right? It represents the direction and the movement toward that direction. Okay. Now, in some case, you need more than just one direction. You need more than just one vector. Right? You need more than just one x. Sometimes you need an array that is more than 2 axes, right? And then you need to, like, suppose that we have just a point, right? Starting from a point. When you have a point, it's like 0 dimension. When you draw a line, you got a 1-dimension data. And a line, think about it as having a set of value like in the vector. Once you have a line and then drawn in 2 dimension, you can have an image, like an image in 2 dimension. Right? From the point to a line to an image. Now how about if we need something more than this, like we need to have an image with a lot of layers. in that case here, it is denoted as a matrix like A, but you have an element K. That element K denote the layers that it has here. This in this course, particularly for this one, for mathematical sense, it is referred to as tensors. That's why in TensorFlow, the widely used algorithm TensorFlow, it is these tensors that they are talking about. So in tensors, they are like 1D tensors, or just a matrix in one dimension, an array in one dimension. 2D tensor in image, 3D tensors. Think about you have an image layer and have multiple layers, I, J, K. 4D tensor is like you have multiple cube, and 5D tensor multiple cube in diagonal in the and then also in the what should I call it? Would be like something like a subspatial domain, like the spatial domain of the spatial domain. 6D tensor. You don't want to imagine something about it, but well, you can configure deep learning to have these type of architectures, and you can see that from the earlier image. Convolutional neural network looks like 3D tensor. Right? So that means TensorFlow would perform computations very quickly based on the tensor processing, matrix multiplication. But instead of just matrix, would be tensor multiplication. Okay, now let's come back to the real world that we talk about vector. Then let's extend it further to the matrix. When you have matrix, you can perform operation like matrix transposition. This T, matrix transposition will will move the index from I to J to J to I. Basically, just flip row and columns. So the transpose of this matrix equal to the right hand side here. Okay, transposition can be done in Python. Just use transpose, np.transpose, and then or if you have data frame, just .t, then you get the transposition of the data frame. For the matrix, use np.transpose, it would transpose the matrix. Okay, let's take a look at the matrix operation as a review. If you have the matrix with the same orders, you can add them together to perform matrix addition. In the matrix addition, you are actually adding the elements, performing element by element addition. So if you have a matrix like this, 1, 2, 0, 3, and 4, 0, minus 1, 5, adding them together, you get 5, 2, minus 1, based on addition, and 8. Okay, that's the matrix addition. The determinants, another topic of matrix. I'm going pretty fast here. To review the concepts that you have already known, but well, maybe let's skim through some of them. If you have questions, though, please ask, put it into the chat. Okay, or if you have questions after the class, like review the contents, and you have questions afterward, post into the group. I will answer the question for you guys there. Okay. Determinant. What is determinant? Determinant is best described as the volume of the matrix. Like what you can think about determinant best when you evaluating the transformation matrix. Let's take a look at example here. Okay. So calculation of determinant can be done by multiplying down. You have the positive terms, and multiply up. You have negative term. Right. What is determinant? Let's take a look at this video.
Let's go back to the basics. Determinants. Let's take a matrix of 1, 2, 0, 2, 1, 0, 0, 0, negative 3. And let's use this matrix to transform every vertex on a unit cube of length, width, and height 1, aligned along the x, y.
What is this? When we talk about matrix transformation, it is actually the multiplication of the adjustment matrix, the transformation matrix, this transformation matrix, and the coordinate. In computer graphic, when you learn about the computer graphic, you will see that you can kind of process the coordinate in the graphical sense. The coordinate in a three-dimensional world into different perspective, right? Those projection can be done by multiplying the transformation matrix to the points, and then those coordinate will be transformed according to the transformation matrix. Okay, so when we think about determinant, let's think about you have this matrix that you are going to transform the point, and the point is like a cube now. And what is that? What is determinant?
After transformation, you'll see that we have a completely different object than we had before. But now I have a bit of a question. How much larger is this new transformed object? We could solve this problem with numerical integration by encapsulating both objects in a larger cube and performing Monte Carlo integration. After integration, we can say that the larger object is about 9 times bigger than the unit cube. Now, let's think of this problem a little differently. During matrix transformation, most vectors will stretch and rotate. However, there are certain vectors that only stretch and do not at all change direction. These vectors are known as eigenvectors, and the amounts by which they stretch are known as eigenvalues. If we align the sides of our unit cube along these eigenvectors and perform a matrix transformation on each vertex in the cube, we'll find a rectangular prism that has not been skewed at all. This makes finding the ratio between the new transformed object and the original unit cube kind of trivial. It's simply the length times width times height of the new cuboid. Now, because we align the unit cube along eigenvectors, and each side of the unit cube is of length 1, after transformation, the new length, width, and height are all eigenvalues. So, how much bigger is the object after transformation? Well, it's simply a product of all of the eigenvalues, which, in this case, is exactly 9. Here, I suppose it makes sense that any object's volume will increase by the amount of stretching in each dimension, which is exactly what we said before. The new volume is a product of the eigenvalues. Now, at this point, you might be thinking that we're pretty clever, but mathematicians have at least one more trick up their sleeve: determinants. So let's do it. Let's find the determinant of our
Right, the determinants of this matrix would be
transformation matrix. It will be 1 times 1 times negative 3 minus 0 times 0, subtracting 2 times 2 times negative 3 minus 0 times 0, plus 0 times 2 times 0 minus 1 times 0, which is equal to negative 3 plus 12, or exactly 9.
That's it. So you can think of determinant as the modifier, as the factor of the matrix. That when you transform the points in the cube, it would kind of modify the volume of the cube to the amount of the determinant.
It's the same as we saw before.
Okay. Right, and you can do the determinant calculation by the mathematical method. In Python, you can use the np.linearalgebra.det to find determinant. Then in Python, you can also perform other scalar operations to add time and do other things. What happens underlying is broadcasting, that Python would perform broadcasting of the 1 times 1 vector of the 1 times 1 matrix to increase it into the size of the M matrix. That is for scalar operation, right? Matrix can be multiplied together, not elements by elements, but in terms of matrix multiplication. In matrix multiplication, you are actually projecting the row matrix with the column matrix, dot them together to get the results. So you have learned that this in, I think, high school and afterward. So when you multiply the matrix, you have to multiply row with the column. This multiplication is actually the dot product between the row vector and column vector, multiplying each element and then sum them all, and then you get the value at that element. Matrix multiplication has certain properties, that it is associative but not commutative. You cannot switch side, but you can group them, multiply them in order according to what you want. In Python, you can use np.dot or np.matmul to perform matrix multiplication. And they are both fine. Okay. Lastly, for the matrix inversion. Matrix inversion, because you cannot putting matrix in division is nonsense, right? Putting matrix in division there, but you can perform inversion of the matrix by what is inverse matrix, right? We can say matrix A is invertible if it has matrix C, that when you multiply C with A, you get I, or A with C, you get I. That means you can inverse the matrix A if you multiply matrix A with the A inverse. Then you get I, or A to the A inverse to A, and you get I. That means that inverse matrix would, when you multiply it or project it to A, then you get I. So finding inversion in mathematical terms, I will leave that to your previous professors that teach you about the matrix inversions. There are quite a number of methods to do so. In calculation, you can use the Python to perform inversion here. Okay, so in summary, there are certain operations that you can perform on the vectors, like scaling, multiplying with the scalar, addition, subtraction, which will perform elements y addition and subtraction. The dot product, which will calculate the projection or the dot calculation between two vectors, and the norm, which is calculating the size of the vector. This is the L2 norm. The L2 norm is referred to as the like you get the element square and then put them into the square root here. This is L2. Later on, you will see other L as well, L1 norm and L2 norm. Let's say the size of the vector in different criteria. Okay. Now, how do we use matrix? You can use matrix to represent data. You can also use matrix to represent the association in equations. If we have a system of equation like this, that it explains the association between x and y, like you might have this from the data that you have input. You have parameters that you want to estimate. These are x and y. And you have input data as 2 and 1. Pairing with 100, and 1 and 2 also pairing with 100, and then you are trying to solve for the value of x and y. Right? This is the system of linear equation. The solving system of linear equation would yield different results depending on the order of the equations that you have, right? Or the order of the coefficient matrix that you have. You can represent the system of linear equation as this matrix form, okay? Like multiplying 2, 1 to x, y, you get 2x plus y equal 100. And down here is like x plus 2y equal 100, okay? Now you can have different types of solutions. You can have the solution that there is no solution at all if your equation is less than variable. Okay, so seeing this, remember this, and then if you build your model and then you have very little of samples but a lot of variables, you can expect to get into trouble here, right? So no solution if you have less data, less equation than the unknown variables. You have exactly one solution if they are equal to one another. And in a lot of cases that you work with data, you have many solutions if the equation is more than variables. You need to estimate the solution instead of having an exact solutions. Okay. In the case that you have the number of equation equal variable, you can solve this matrix by finding inverse. By representing this as ax equal b, you can multiply the inverse of a to this matrix, and then you get x equal a inverse and b. Right? This is what you learned it back then. So here I created matrix A, and then here's the matrix B, and then multiply the A with multiply B with inverse of A, and then get results of 33 and 33. Right? Simple enough. If you have equations of data more than variables, in lots of data science applications, this is the case that you have often encountered. Okay, for example, in a data set empty cars, there are 32 data points and 11 variables. If you use one variable as output, you still have 10 variables as predictors, and then you still need to find 10 parameters, 10 coefficients associating with each predictors. Okay, let's take a look at these simple examples. This is a multiple regression examples. Suppose we have the data like this, x1, x2, and y, and we want to fit them into this equation, y equals c1 x1 plus c2 x2 plus c3. Okay, we got x1 and x2 and the coefficient 3 unknowns, and we have 4 equations. If we put the data into equations, we have this set of equations, right? This is the system of linear equations, but well, you have more equations than the unknown. Doesn't mean that you cannot find the answer, but you need a way to estimate for the best solutions of C1, C2, and C3 out of this. Okay, there are many ways to do the job. The one that I will just show you here is the method called pseudo, because you cannot inverse, you cannot multiply it with inverse. There are no inverse here, but you can find the pseudo inverse. Pseudo inverse take into consideration of the rank or the order of the matrix. That is, A is n times m, which is not a square matrix. So we have something like a b equal y is like output, and a is a coefficient, and b is something that you want to know. You can find b by first, because it's not square matrix, we need to make it square. How? We can multiply both sides with A transpose. Once you multiply this with A transpose, this with A transpose, then the A transpose times A will be a square matrix, right? If you wonder if that is the case, just imagine this, like suppose you have 4 times 2, and then you multiply it with 2 times 4, the resulting matrix will be the dimension of 4 times 4, right? It will become square matrix. And once this becomes a square matrix, you can multiply the inverse of it to the whole bunch. And this would cancel each other out to become I. And here is the formula that you have to do in order to solve these equations. Okay. So here, let's implement it. Here I have the array of A and B, and I want to find the X and the C1, C2, and C3. How do I do? How do I work on that? So what I did here is to use the P inverse. P inverse is a pseudo inverse of A multiply B. You get 3, 5.5 minus 1.5. You may call me cheat because, well, P inverse is like find the pseudo inverse for you guys. So here is the full form. This is the multiplication of A transpose and A, right? And then matrix inverse of the A transpose and A, and time A transpose and time the Y, the output, and then you get the similar values 3, 5.5, and minus 1.5. Okay. You can also solve it another way using the linear algebra and least square method. The least square method would solve using the similar technique. And then find the solution like this. Okay. Almost done for the matrix and vectors. I think, yeah, almost all of that. Okay, some of them you have already learned. So if you are not sure about the concepts, try to review the old contents, or you can ask here or ask in the groups. Okay. We call a linear combination a set of vector, a linear combination of vectors. Suppose we have a vectors v1 to vp, and we have coefficient c1 to cp. Say if we have y equals c1 v1 c2 v2 to cp vp, we call this a linear combination of vector because they are linearly combined. That's why they are called linear combination of vectors. Why do you need to know this? Is because of the next concept. The linear combination of vectors, suppose you have a vector like this in linear combination. If you can equate this c1 to cp to 0 and has only and this work only in the trivial solution. What does that mean? You cannot combine the vector and make them 0. If that is the case, then it means that these vectors are linearly independent of one another. They are not dependent on another vector. Independent. For example, like this one, c1 0 and 1 plus c2 1 and 0 equals 0. Can you find c1 and c2 that are not both 0 and work? You cannot, right? Because they are independent of one another. One is going to like x-axis, another moving into toward like y-axis. Right? So that's the case. And in many data science applications, we want to determine this, because if in some cases that you find the solution here, it means that the vectors may be collinear or redundant. You might not need them in your model. And that's the case for the linearly dependence. If you can find solution, the non-trivial solutions in this case, that there exists the values that makes this equation true, we usually call this the collinearity, that they depend on one another, and you can kind of remove them out in from the equation. Although for deep learning you might not have to do so by yourself, but well, this is the concepts of independence and dependence. Now let's move on. The concepts of norm in vector. Like norm is referred to the size of the vector. Right? We usually call the function norm as the norm of order p. Right? The norm of and usually we use like L1 and L2. Right? The norm of order p can be found by this equation. It's actually a summation of the value to the power of p, and then on 1 over p. Right? So for the L1, L1 norm will be the size of the vector with respect to each of the side of the vectors, each of the eigenvector, each of the coordinates distance. L2 refers to something like Euclidean distance, can be found by the dot product between two vectors, and then you get. It is actually not true. Have to have the square root here as well. I think it has to be something like this. Yeah, to be correct. Because the L2 norm will be the square root of the L2 norm will be the square root of the x1 square plus x2 square plus dot plus xn square. So the dot product between them would be the square of the norm, right? This is the L2 norm. Next, in terms of vector, we call a vector a unit vector when it has a norm of 1, has the L2 norm, the size of 1. Okay, it is usually used to represent the direction of the direction because it has a size of 1. We can find the unit vector along a certain vector by taking that vector and divide it by the norm of the vector. Then you get the unit vector moving in that the same direction as that vector. In Python, if you want to find the unit vector, you can do it by taking, like, this one is the vector 3, 5, and then if we divide the vector v by the norm of v, we get the unit vector of v. This would move in the same direction as 3 is 5. Knowing the unit vectors allow us to determine that the vectors may be, well, when we have vectors, we can determine whether the vector is perpendicular to one another. We usually call this perpendicularity of the vector as orthogonality. Like, the two vectors are orthogonal if when you dot them and then you get the value of 0. Why is that the case? Think about that vectors are, when they are perpendicular to one another, they are not related to one another. Like the vector that move in the direction x and the vector that move in the direction y. And when x move, it doesn't affect y. When y move, it doesn't affect x. We usually call this orthogonal to one another, or they usually are unrelated to one another. Right? Like these two vectors, 2, 1 and minus 1 and 2. If you perform dot product between them, you get the value of 0. And these are orthogonal vector. The orthogonal has certain meanings. You can think about orthogonality as, like, in the numerical sense, they are just not correlated, not related to one another. But think about it as, suppose that you talk about text data. If you have two vectors representing the keyword, extracting from two different documents, and then when you calculating the orthogonality between the two vectors, you find that they are orthogonal, right? When you dot them, you get 0, and that would mean that the documents belonging to different topics potentially. Okay, so orthogonality is used in lots of concepts in data science, like SVM, in finding similarity and other things, in Pca as well. That we will talk about that later on. Okay, the unit vector and lines. If you have a line like this, 2x plus y equal 10, here is the line. You can get the vector that is orthogonal to the line by just taking the coefficient. Like the 2 and 1 would be a vector that is orthogonal to the line, perpendicular to the line. This is 2, 1. So that's all for the review of the vector concepts. Any questions before we move on further to the next topics? Mostly these are the things that you have already learned in your undergrad level. Some of them might be before that, might be in your high school level. And I know these are quite a long time till now, but you will have, this is a chance that you use all of them, and you'll see later on in the subsequent lectures that some of these play very important roles in learning, deep learning. Any questions about the vector and the matrix before we move on to the next topic? All right, no question. Then next is the Eigen Decomposition. What is Eigen Decomposition? What is decomposition? The concept of decompositions comes from that we can think of the data as the combination of multiple patterns. We can extract those patterns out to have different types of consistent patterns. there are many techniques that allow you to extract those out, and some of which relies on the mathematics, some relies on statistics. In a lot of machine learning techniques, we use statistics to identify which variables are important. Those are also decomposition, the regression technique. Now, what is Eigen Decomposition? Let's take a look at the concept first, and then it might allow you to see that Eigen Decomposition actually plays very important roles in the development of Google, in the graph theory, in other things. So let's consider this situation that we are talking about unemployment rate, and then we want to describe the unemployment and employment, the rate of unemployment and employment. We want to create a population-based model, like in game theory, using the model called Markov Models. The Markov model explains the transition between state as the dynamical process. What does that mean? It means that when you are at one state, you have a chance to transit to another state. Okay, so suppose that you are currently unemployed. An individual is currently unemployed. There is a probability P for you to be employed in the next week, and 1 minus P to stay unemployed. If the individual is employed in a certain week, there is probability Q to stay employed, and 1 minus Q to be unemployed. Okay, hopefully I'm not confused now. So let's see if the variable is correct here. So we have here, if we are still unemployed, then probably P to be employed and 1 minus P to be unemployed. Okay, this is correct. If at a certain week and that individual is employed, then probability Q for stay employed. Q for stay employed. Q for stay employed. Maybe I should use this one, so it will stick to the slide. Let me. Q for employee, 1 minus Q for transition to the unemployed. Right, and then we can write a Markov model for unemployment like this one. Suppose we have X as the individual, the ratio of individual being employed at week T, and YT becomes unemployed. Then at a certain week, the number of employment for XT would be QX here, Q times X. So X is the number of the ratio of individuals that is employed, right? This is XT, so I should write like this. Let me write it here. Employed is X, unemployed is Y. So the number of X would comes from, just look at the arrow sign. X would come from transition for unemployed to employed, so P times Y and Q times X. That's why we have this X at T plus 1 would be Q times X at T and P times Y at T. And Y at time T plus 1 would be 1 minus Q times X and 1 minus P times Y. Okay, this is called the dynamical system because it's changed according to times. Now we can represent this as the as matrix like this. So it means that V at time T plus 1 equal A VT. Right, and V at time T plus 1 is X T plus 1 Y T plus 1. V at time T is X T and Y T, and the coefficient is Q P and 1 minus Q and 1 minus P. Once we reach this stage of the model, we can determine the behavior of this dynamical system of this game theory to determine the long-term state, or this is called the equilibrium, whether there is an equilibrium with the model. How do we determine that? right? Computationally, you can multiply the transition. Think about that, because if you multiply it 1 time, that's 1 week. 2 time, 2 week. So if you multiply it t time, then you get the transition for t week. Suppose that at the start we have the p as the probability of what? P is probability of getting job, right? Yeah, of getting job. Q is the probability of retaining job. We have value of P and Q like this one. Have 99% to retain the job, has about 14% to get the job. And then at the current rate, at the moment, suppose that the x0 is 0.95 and y0 is 0.05. These are the unemployment rate and employment rate. After 100 weeks, we can make projection on what would be the values. Right. But you don't really need to do this. You don't need to multiply it 100 weeks or 1,000 weeks, because you can actually decompose this matrix and find eigenvalues and eigenvectors, and then know the equilibrium, the values, if you multiply it 100 or 1,000 times. Okay. Eigenvectors has been used in auto technique as well. Eigenvectors are something like the core axis of the matrix, of the vector of the data. So it's best to imagine in terms of the Pca technique. The technique called Pca, or principal component analysis, is a technique that allows you to identify the principal component or the eigenvector of the data. And instead of representing data as it, you can projecting the data onto the new axis so that it would be represented better than the current coordinates. For example, suppose you have the data in x and y like this one. This is x, the x-axis, and y-axis. And you can see that x and y are somewhat collinear. That they are like, if you look at the dot in the scatter plot, they are kind of going in the same direction as one another. So technique like Pca allow you to identify the allow you to identify something like x prime and y prime, the axes that are not depending on one another. These are the eigenvectors of the axis, and the eigenvalues are the spread of the data. And Pca allows you to identify this and then projecting each point onto the new axis. Right, so this is the reasons that eigenvector and eigenvalues plays quite important roles in machine learning. That is because it allows you to transform the data from one domain to another domain that is easier to use. And actually, deep learning do the same thing. Deep learning transform the data from the raw data domains into the transformed data domain that is easier to classify. And we will see that later on in the concepts afterward, in the latter classes. Eigenvector is also used in applications like eigenphase. That is, it decomposes the phase into the composition of the template phase or the eigenphase. And then you can use the coefficient to identify whether the phase that you are receiving is actually similar to the phase that you are trying to compare with or not. Okay, eigenvector is used in social network analysis to identify the nodes that are important. By representing the graph as a matrix, you can identify which node is likely to end up with if you were to randomly walk in the network. This is called Google PageRank. Google used this structure to identify which web page is likely to be the prominent web page by analyzing its structure. Okay. Eigenvectors and eigenvalue plays an important role in linear transformation as well. So if you transform, I have a matrix to transform the point this matrix actually transform the points 1, 2 to 5, 6. But you can see that after transformation, the matrix, even from this vector to another vector, is actually the scaling of the values on the axis of x and y axis. Okay, but the direction of x and y axis stay the same. The x and y axis are known as the eigenvectors. That is, when you make the transformation, it doesn't change, but the value at that axis changes. Okay, so in the formal definition, the eigenvector can be thought of as a vector that when you multiply the transformation to the vector, multiplying transformation A to vector x, it results in lambda x, where lambda is a scalar values. What does that mean? It means directions stay the same no matter what values that you multiply the vector with. It would just translate, it would just enhance, but in that same directions. Okay, we call this lambda here of A as an eigenvalue of A, and x as the eigenvector. Okay, now let's take a look at some examples on eigenvector and eigenvalues. Here is an A. We have A as 1, 2, minus 1, and 4. And if we were to multiply A with 1 and minus 2, let's perform a simple calculation here. Take row, multiply by column. This is 1 times 1 minus 2 times minus 1. That's why we have the value of 3. And then 2, 4, and 1 minus 2, which is 2 times 1 and 4 times minus 2, which results in minus 6. So pulling 3 out, you get 3 and minus 1, 1 and minus 2. So it means that after multiplication, you end up with the same vector, but the transformation matrix transform into just a single value. Here, we call 3 an eigenvalues of A, and vector 1 and minus 2 is eigenvector of A. Okay, an eigenvector of A with corresponding eigenvalue of 3. Why do we need eigenvector? Why do we need eigenvalues? And how do we find these eigenvector and eigenvalues? If you think back, some of you may come from engineering backgrounds, and you may have, or if you take a physics course in undergrad level, you might have remember the technique called Kirchhoff voltage law and Kirchhoff current law. And you might have encountered a technique like node analysis and mesh analysis in the electrical, in the I would say in the circuit analysis course, or in physics course when you learn about electricity and the circuit. When you study about the behavior of the signal like that, you are actually identifying the eigenvector to get the value of something like e to the eigenvalues, to express the behavior of the C and the L in the circuit. But if you have come from other areas, what we are talking about is actually the behavior of the dynamical system, of the mechanisms in the real world that kind of I would say that kind of transferring energy from one point to another point, and there are certain exchanging certain energy with one another. So that means so for this case, we have this a matrix that can be represented as a scalar value. We call this an eigenvalue, and the vector here, think about it as the core vector of this matrix. Okay, how do we find the core vector of this matrix? We can find the core vector of this matrix by deriving it from the characteristic equations. So once if we have this coefficient right? And we want to find the characteristic equation of this matrix. We can determine it from this by moving the lambda x from this equation to the left hand side and then pulling x out. We have the a minus lambda I equal x. For a minus lambda I equal x to become 0, this a minus lambda I has to have determinant of 0 because it would need to scale x to 0, right? So we have the det of a minus lambda I becoming 0. And then determining the value of lambda, you get the eigenvalue. And by substituting lambda into 1, you get the eigenvector corresponding to that. Let's see if it works in our case for 1, minus 1, 2, and 4. For 1, minus 1, 2, and 4, we have it here. And then minus of lambda and the identity matrix, this would be lambda and lambda. Subtracting it out, you get 1 minus lambda and minus 1, 4, and 4 minus lambda. Calculating the determinant of these differences, you get this multiplying down become plus, and multiplying up you get minus, right? Have 1 minus lambda and 4 minus lambda plus 2, because multiplying up you have minus, and with the minus you get plus. Then for this one, you have the lambda square minus 5 lambda plus 6. Just multiplying them here. And then take factor. This is lambda minus 3, lambda minus 2. That means there are 2 eigenvalues for this matrix, 3 and 2, right? Or the 2 root of this equation. Once we know this, we can then determine the eigenvectors of this equation by substituting 3 and 2 into the equation 1. Okay, so for that sense, we have this a minus lambda 1 I x equals 0. Lambda is 3, plug it in, and then you get this 1 minus 3 minus 1 x1, 2, and 4 minus 3 and x2. This is minus 2 minus 1 x1 minus 2 1 x2. So you may wonder, well, they are the same equation anyway, right? It is minus 2 minus 1 and x1 x2. When you multiply it in this way, you get minus 2 x1 minus x2 equals 0. So that would mean x2 equal minus 2 x1. Or if you multiply it like this, you get 2x1 plus x2 equals 0. So x2 equal minus 2x1. They are the same. Right. So for this one, it means that you have relationships between x1 and x2. You can make assumptions here. Suppose that you assume that x1 equals 1. Then x2 would become minus 2. Right. x1 is 1, then x2 become minus 2. So that means you have eigenvector of 1 and minus 2. Why can you make assumptions like this? The reason is because you need to multiply it with certain coefficient and anyway when you use it. So those scalar value multiplying with eigenvector, it will scale it out. So you can just make assumption that where one value is 1, then what would be another value here? Then you get this as minus 2. Right, let's find another one. Okay. Another eigenvector for this one can be found by substituting lambda 2, which is 2, into the equation 1. Then we get 1 minus 2, and minus 1 is 4 minus 2. Then you get relation like this one, which means that x2 equal minus x1. If x1 is 1, x2 is minus 1. So that means eigenvector is 1 and minus 1 for the eigenvalue of 2. Okay. You can use Python to solve the equation and find the acid, like the 1 minus 1 and 2 4 using the Eigen vector decomposition. You get eigenvalue of 2 and 3, eigenvalue of 2 and 3, eigenvector of this. Now is my question. Well, we get 1 minus 2 and 1 and minus 1, but when we use Python, we get this minus 0.707 and 0.44 and 0.707 and minus 0.8 minus point, oh sorry, we get this minus 707 and 707, and then this one minus 0.447 and 0.447 and minus 0.894. Why not 1 minus 1 and 1 minus 2? Can anyone answer this for me? Put it in the chat. If you have question, what have I done here? So the technique known as Pca that I talk about require that you have like a tabular data. It usually reduces the data into principal component. When doing this, it needs to calculate the covariance so that you have the square matrix. And then from the square matrix, it will perform the eigenvalue decomposition so that you have a set of eigenvalues and eigenvector according to that. And then principal component is actually the projection of the data here with this eigenvector. Right. Y minus 1 and 1. Oh, sorry. Y minus 0.7 and 0.7 and 0.4 and minus 0.8. Are you still there? Please answer so that I will know that I'm not alone here. Why is that? Make a guess. Why do you think this is the case? Any idea? Correct. Unit vector. Just because the function here would give you the unit vector. So this is the unit eigenvector. It doesn't matter because whether it is just 1 minus 1, 1 minus 2 or the eigenvector, a unit eigenvector, they are still on the same direction. And when using with like Pca, using with other techniques, directions matters more than the scaling values. Okay. Correct. Right. So yeah, these are still the review. Don't worry. When go to the deep learning, you will definitely have to use them. Now you have to worry. If you pick up the book, come on. If you pick up the book and go to like chapter 2, you will find them here. All about vector decomposition, about what I'm talking about, with assumption that you have already known. You have already known certain concepts. So I'll try to kind of digest that into like a simpler version, hopefully. Yeah, hopefully that's the case. Okay. Now the last topics. Let's take a break. I know it's quite a lot in terms of the review. Let's take 5 minutes break. And 8:08, we will resume on the probability theory. Break. เสร็จอะไรล่ะถามตะวันบอกเล่นเกมไม่ได้เหรอบอกว่าให้ตะวันไปทำงานบอกตะวันทำตั้งเยอะแล้วเนี่ยทำ4 หน้ามีอีก8 หน้าในสารบัญจากสารบัญ8 บทนั่นน่ะเขียนดีนะในบทที่1เนี่ยแต่ว่าไม่รู้จะเสร็จเมื่อไหร่เขียนดีอธิบายดีมาก เหนื่อยเด็กจะรู้เรื่องไหมเนี่ยว้านนิดนึงมันจะรู้เรื่องปีนี้คนลงน้อย เพราะว่าครั้งแรกเข้าสอบไม่ทันต้องนั่งเช็ดที่นี้ก็พอโทรมาลองช้อปปิ้งก่อนไงครั้งแรกมาช้อปปิ้งแบบมานั่งเช็คอินดูก่อนว่าเป็นยังไงตัดสินใจลงพี่มาครั้งแรกไม่ได้สอนเนี่ยก็เลยแบบก็มีพวกที่รู้จักอยู่แล้วที่มาลงที่เราแล้วที่ตรวจสอบนี่เลย9 คนโอ้หูอื้อฮะเก็บแล้วยังยังไม่ตักเลยเดี๋ยวพี่เปลี่ยนนะไม่เปลี่ยนฮะเปลี่ยนถังเดียวได้เท่าไหร่ไม่เปลี่ยนถังให้ใช่ถามตะวันแล้วแหละตอนยองจังพี่เป็นจัดการโอ้อื้อกินข้าวใช่ไหมเป็นไงบ้างร้านนี้ก็ไม่ค่อยอร่อยใช่ไหมเฉยๆสู้ร้านนั้นไม่ได้ร้านนั้นก็ปิดยังเลยไม่ปิดหรอก8:08ได้ยัง2 นาที ต่อสงสัยปล่อยแล้วก็หายไปแล้วมั้งตอนนี้เที่ยวที่อื่นต่อละOkay, the last one I think right this will be the review of probability theory and the related theory on probabilities.We'll use it later on for sure, like expected values and others in the developments of the deep learning model or on the neural network models. Probabilities plays quite important role in AI because you want the AI to be able to generalize from data, right? We use in AI we use probability so that it can make decisions based on uncertainty, and it can also analyze based on the statistical patterns of data. Usually there are uncertainties in real world. The source of uncertainties can come from many things. It can come from the system itself, like if you model the human decisions can be varied. It can be because of the system contains certain variations from nature, like you model the stochastic behavior of the weather patterns. Or the uncertainty can occur if you have incomplete observations, Like you have an image and you have the other object obscure an image. You want system to be able to generalize from the remaining data that it has. That it need to justify only to guess what would be the thing that is obscure. So that's for incomplete observation. Uncertainty can come from modeling itself. That like not all variables are included, and that create uncertainty in the models. The definition of uncertainty and probability can come in two kinds. One kind is frequentist probability. In frequentist probability is defined as the when you observe the observation in many times, you can find the number of times that it occurs, like probability of p. Right. But this type of reasoning has a limited application, because in some cases you might not be able to find that occurring, like in the risk analysis, in the failure analysis. The chance that it happens might be low. So encountering the event might not be practical. Another probabilities come from deduction. This is called Bayesian probability. In Bayesian probability, you can assess probability of event based on the dependency between the events. We usually call this Bayesian definition of the probability. Like we have a certain degree of belief that patients might have the value between 0 and 1 to have flu instead of just having 1 or 0. In frequentist, usually you would count the number of times things happens, and then you get the probability. In Bayesian, it's thought of as every individual has a certain degree of values, certain probability that could have that event. Okay. So those are the definition of probabilities. When you have events that have probability associating with it, and those events can produce values, we would call those values, those processes that produce value, random variables. Random variables is a process that can generate different types of different values out of the process. So it can be two choice, like churn and unchurn. It can be the count, like count number of car passing through the university per minute, or it can be like the number of customer coming through the store for each hour. It can be a continuous variable as well. This random variable, it can take like the temperature and sensor data, because it also contains certain uncertainty there. So random variable can be discrete or continuous. With these random variables, and so think about random variables as some value that contains certain chance to happen. We can explain the random variables in terms of probability distribution. The probability distribution describes how likely the random variable takes on certain values. So this can be explained in terms of discrete variable and the continuous variable. Let's take a look at here. For discrete variable, we have the probability distribution in forms of the function called probability mass function, PMF. Probability mass function denote that the variable would take a certain value, like x equal x, and it would have probability px associating with it. For example, if x is with the property of 1 indicating x equal x for certain and 0 not certain, right? But x can take certain value depending on the thing that you are considering it. For example, if we considering the event of x equal customer churning, leaving the company, and not churning, right? Then the PMF of this distribution would be P churn equal 0.1, for example, and P not churn equal 0.9. This is called the probability distribution that it takes on the certain event. Now, if we have like multiple events that occurring at the same time, we can have the joint probability distribution, the distribution of the two variables altogether. Like for this one, we have P of X and Y. X can take a number of values, Y can take a number of values, and in combination, they would have the probability associating with the chance that these observations would happen with certain criteria. That is, the probability must be more than 0, and the summation of all of these has to be 1. This is called the joint probability distribution, because it explains the chance that you observe a certain combination of X and Y, and you have value X and Y, and the chance that it happens. That means X and Y are the random variables. PMF has certain properties. That is, the value of the probability of each value there would be between 0 and 1. So it would take, that means the probability of having one value would be between 0 and 1, right? And when you combine the value of all of the combination, you get value of 1. That is the universe. The probability of universe is 1. Just like the thing that you learn in your statistics and probability in your undergrad degree. This is for the discrete variables. For the continuous variables, instead of calling it probability mass function, it's called probability density function. They are similar, though this one would be continuous. That means value of px, value of probability would be more than 0. But instead of summation, if you integrate the density function, you get value of 1. Examples of probability density function, the PDF, is the normal distribution. It looks like this one, right? This is the standard normal distribution. If you integrate the standard normal distribution, you get the value of 1. Right? This is the whole probability value when you combine all the chance that thing would happen. Okay. You can find the probability of that occurring from a certain region. So when you take one value out of the PDF, you are actually getting px delta x. That means you are getting just one value here out of this. This is like the chance that this value would happen when you take it out of the distribution. But usually in the continuous value sense, getting just one slice of value is difficult because 2.0 and 2.1 is not equal, right? So finding probability at 2.0 is not close to 2.1. So instead of that, we can find the probability of the range of value by integrating the area under the curve of the PDF, and then you will obtain the probability. Okay? Right. So this is like how you obtain the probability from PDF. There is a probability when you have the joint distribution. If you were to eliminate one axis out, we would call this a marginal probability distribution. It means that you are considering just one variable at a time. Right? This is called a marginalization process. That is, you kind of summation of all probability on one axis, integrating by one axis. This marginalization is used a lot in the Bayesian statistics. So if we do something like Bayesian belief network or the Bayesian deep learning types, you probably encountering this marginalization process. But for us, luckily, we will not begin with those. That will be a little bit more advanced. So this is a process called marginalization, or eliminating one axis out of the distribution. Then you get like if you think about something like going to university. Marginalization, you know that university is on the plane, right? So it has X and Y. Marginalization is like the process of viewing the university from the front. Then you are eliminating the depth because you are seeing just from the front. So it means that in computer graphics always marginalize one axis so that you can perceive it as two dimension. I don't know if this would explain things better or not, But yeah, the marginal probability distribution works the same way. That is supposed to have joy distribution. If you want to know just how much it would change in how much thing would happen in one direction, you can marginalize the other out and then get just one axis. Right? This will be p x equal x, and then you just marginalize y by summing them, and then you get the pop of x equal x would happen. Right. Okay, so those are the basic probability. Then we now move on to a little bit more concept on probability theory. This is called the conditional probability. Conditional probability is the probability of certain events given that you know that certain thing happens, given that certain condition happens. So this is like p y equal y given x equal x. This comes from the joy distribution of y and x divided by you know that x happen, right? Px equal x. This can be explained in easier in the set term. So let's look at this Venn diagram. In this Venn diagram, you have A and B. If we talk about just P of A, P of A would be the proportion of A divided by the whole thing, right? The proportion of A divided by the whole thing. This is P of A, all the chance that A would happen. Sometimes we would call this a prior pop. The prior. Now, PA given B, what is it? PA given B is still a P of A, but you know that B happens. So when you know that B happens, you are trying to find the joy distribution of PA intersect B, which is the intersection between A and B, divided by PB. What is PB? Think about PB as the area of B here. So you are taking the area of A, dividing by the area of A intersect B, dividing by the area of B. So what you end up with would be the proportion of A that is in B, right? So this is the conditional probability. The conditional probability can be used in the latter sense that we will talk about prediction, that you want to predict even A occurring given that you have certain data, you have the model, and then compare that with the prior, and then you will see whether your prediction is better than the prior or not. Okay, so here is the definition of conditional probability. Okay, conditional probability has the chain rule. Okay, I did not erase it out here because I don't want to write it again. So this is the chain rule of conditional probability. So you have this joint distribution. You can take one out. Take the one prior out, and then you get the sum, the multiplication of the conditional pop of the rest of that event I given the rest. If you take another prior out, you get like P of x2 given x1, and then the conditional pop of the x3 to xn, and then x1 and x2. So these are the basis of Bayesian theory and Bayesian network. Seeing math like this might scare you. So let me explain it in terms of the table. For this one, this is like a table with n column. An n column table. An n column table, if you were to store it as 0 and 1, you have the total combination of 2 to the n, right? That means this table will be quite large if you want to store all of the combination of these variables. However, think about this table. Just one variable, right? Px1. Suppose that you have 0 and 1. Then this is just the size of 2 just the size of 2. 2 to the 1 is 1. And this table will be the size of 2 to the I minus 1. So it means that you are taking, when you take it off here, you reduce the number of, or the size of the table that you need to store 2 times. Instead of having the 2 to the n table, now you have this 2 and 2 to the n minus 1, which is a lot less than 2 to the n. Right? So the number of data, the size of table that you need to store is reduced quite a lot. Bayesian relies on this concept to decompose the joint distribution into multiple dependency of the table. So instead of storing a large joint distribution table, it stores just like a piece of fact that suppose like seeing high temperature and having COVID, and then you get certain probability. Seeing low temperature, have COVID, has certain probability, and then this would depends on like whether you travel to this country or not. So you can derive it as rule and store it as the dependency table without having to store the joint distribution table. So this is the good things about the chain rule of the conditional probability. It can be applied to the Bayesian technique. So just if you study Bayesian, come back to this concept and review it again, it will help. For us in this course, we are not doing the Bayesian inference or the Bayesian technique in detail yet. So this is just a review at this time. In the advanced deep learning technique, there are techniques that combine the Bayesian inference with the deep learning. Because deep learning relies on calculation of the patterns, but if you want to make inference, sometimes you need to kind of encapsulate deep learning model with the Bayesian inference, and it will allow you to kind of doing the reasoning. If you want to study about this more, about inferencing reasoning, I would suggest the topics of Bayesian network. I try to study that topic. It's not difficult. Although mathematical is quite scary, but in terms of data, it's actually quite simple. Just some table, and then you just multiply table together in the end. Right? But the derivation of the technique is quite complicated though. Right. So next topic would be the expected value. We call the expectation of the of some random variable, some function, as the multiplication of the probability and the random variable. Fx is the random variable of the function that produce value, and Px is the probability of that one. So expected value in discrete sense is summation of P so the chance Px is the chance that thing happen and the outcome. While in continuous sense, it's the integration of probability and the value. So this is expected value. Expected value has linear property. That is, you can find expected value of a formula of the combination as the combination of the expected value. So basically, if you add these two population together, each has its own expected value. The combination of the population will be getting expected value and add them together. That is expected value. Now, if we talk about the expected value at the order of 2, this is the variance. You can think of variance as expected value measures something like the centrality of the distribution. Because you are multiplying the chance of thing happen with the value, then you get the kind of estimate of the mean, right? The mean of the distribution, the mean of the value of that distribution. Like if you have a chance that customer would buy things by 0.1, not buy by 0.9. If customer buy your product, then you get 100 baht. If not, then you lose minus 10 baht. Then in combination, the expected value would be 0.1 times 100 and minus 0.9 times 10. and this would be equal to 10 minus 9 equal 1. That means the expected value is 1, so you can expect to get profit of 1 baht per customer. Right, so this is expected value. This can be applied in many sense. You can apply it to the result of the model. You can see that the technique also many of them derive based on the expected values. Okay. Now, well, you know mean, then next must be the variance. To measure the variations of data. Variance is actually the expected value of the difference between the value itself and the expected value and the mean. So you are trying to find the expected value of the difference square, right? The size of the difference, and this is called variance. If variance is low, it means that f is closer to e, the cluster is tight. If variance is high, then it means that f is farther from the mean, right? So if you take the square root of variance, then you get standard deviation as in the statistics. Okay. And the terms covariance refers to finding variance of two things together. So covariance of function f(x) and g(y) of two variables is taking the expected value of comparing in one axis, fx to e of fx and gy to e of gy. Looking at it this way, you might, so for this one, covariance would measure whether they goes in the same direction. For example, if the value go in the same direction, like x and y, high value of x would pair with high value of y, low value of x would pair with low value of y. That would mean if this is the mean of x and mean of y, ignore g and for the moment, then you get a value here. If f is more than mean and y is more than mean, then multiply them, you get positive value. If x less than mean, y is less than mean, multiply them, you get positive value, right? So this is like an average of the difference. So you can estimate whether they are covary together or not, or whether they are negatively covary with one another. This is covariance. You can see that this is like correlation. Actually, correlation is covariance in the normalized way. Right? So correlation is actually measuring covariance divided by the norm of the vector in x and y axis, and then you get correlation. You can see that it's kind of tracing the root coming from the same stem. Covariance can be computed to get the covariance matrix. The covariance of x, of the matrix X, suppose that you have the matrix of multiple column, multiple column, then the covariance matrix is the covariance of each column, right? So it's like the covariance of each column, and the diagonal will be variance value. Right, so this is the basic concept of probability that, well, we will use them time and times. And you can see that learning machine learning would require you to definitely get into this probability theory and statistics. In any case, I use it every day. Actually, I just post something about statistics, like a test of virus, right? That is the confidence interval has certain assumptions that must not be ignored. And because it relies on normal distribution or the t distributions, it relies on standard deviation and mean, which if the data is not normally distributed, that's not valid. In any case, just take a look if you are interested in that. Okay, let's take a look at some distribution that we will find in the deep learning class. The first one, the Bernoulli distribution. In the Bernoulli distribution, we have a distribution that can take the value of 0 or 1. Right? And then you have a chance to get into that value. So px equal 1 would be equal something. Px equal value would be 1 minus that phi equals certain values. And in the Bernoulli distribution, you can take 0 or 1. So the chance that you will observe this would be x time would be phi of x and 1 minus phi of 1 minus x, depending on how many times that we are talking about here. And the expected value of x would be phi, and the variance is phi and 1 minus phi. This is like the distribution for 1 and 0. But in deep learning, in machine learning, instead of calling this a Bernoulli distribution, it is called a binomial distribution, taking two value, one of the two. Okay, so it's the binomial in machine learning. Then we have the multi-nully distribution, or the categorical. You know this as the multi-class classification. The multi-nully distribution is a distribution that would take a single discrete value out of k different state. Okay, this is called a multi-nully. So a multi-nully would can be parameterized as the parameter as p. P would be the vector that telling pi would say that the chance that you would belonging to that class. So think about this as when we learn, this would be the results of the softmax function, and then you get this multi-nully distribution or multi-class distribution, and then we can pick like the highest one out. So multi-nully is often used in referring to the category of the objects, and the highest one refers to as like the most likely object that could occur. Okay. The next distribution is the distribution that has often encountered in statistics, the Gaussian distribution, or the normal distribution. Gaussian distribution or normal distribution consists of this exponential function. Think about this. Exponential function has the highest value at the value equals 0. That means this one will be highest if x equal mu, right? Because x equal mu, it will be 0. If x is not equal mu, then it will take it will has some value. Once it has some value with the negative sign, this would reduce the values of exponential quite a lot. That's why we have this reduction here, inflection like this from this exponential values. Sigma control the shape of the distributions. It scale the value in this sense, the value itself, and it also scale the expansion of the exponent here. So mu then would be the center of the peak, while the sigma would control the spread of the mountain. All right, this is the normal distribution. Okay, this is a particular case called standard normal because mean equals 0 and the standard deviation equal 1. Okay. Normal distribution when you have multiple variables, or let's put it this way, when you have a vector. When you have a vector, not just one value. And when we talk about distribution of the vector, it's not just one value anymore. So the distribution of the vector in the normal sense would be a mixture of, not a mixture, I would say multiple distribution, multiple normal distribution. And that multiple normal distribution would have multiple mean, vector of mu, and has certain dependency, certain covariance between them. This is called the multivariate normal distribution, or the distribution of multiple variable. So the difference would be that instead of having just sigma, you have this determinant of sigma to determine the size of transformation. And here, this is still x minus mu, but instead of having the 1 over sigma, you have sigma inverse. And the reasons that you have this x minus mu again and x minus mu transpose, this is to denote the square. Okay. So this is the multivariate normal distribution. This multivariate normal distribution can express dependency between the distribution by having the covariance, having the value not in the diagonal line. If it has certain dependency between them, the covariance would have certain value, and when you multiply it in this sense, it will contribute to the distribution. Right? One distribution will contribute to another distribution. And this is for the normal distribution. For the exponential distribution refers to a distribution that is using exponential. In deep learning, sometimes we want to have probability that have sharp point at 0 and then reduce at higher values. We can use exponent function in that case. This is exponent function. So when x increase, lambda would when x increase, the value would decrease. Lambda would control the rate that it would decrease. Okay, this is called exponential distribution. When to use this? Sometimes we use it for example, for controlling the learning rate, so that you have large learning rate at the beginning, smaller at the end. Yeah, so this is for the exponential function. The next one is the Laplace distribution. Laplace distribution has this formula. Actually, it's quite similar to normal distribution. If you look at this case, the difference is that this is absolute instead of square. So when it's like that, Laplace distribution would be sharper than normal distribution. I think this is the last one. The last one is the Dirac distribution, also known as impulse. Dirac distribution has a special property that it is the distribution that has only value in the value that is located. Sometimes this is denoted as an impulse. It means that it happens at this time, not any other time. Right? The Dirac delta has certain property that when you integrate it, it has the value of 1, and at this point it has the peak of infinity, but the width of 0, approaching 0. This is usually used to denote when you take the value out of the continuous distribution, or well, when you use something like convolution and denote it as the discrete level, their delta would come out in that way. Or when you take derivative of a sharp, if you take derivative of a u function, if you d by dt of this function, it gives you the delta of x. This is at 0. Yeah, so this is the relationship which is important in the latter mathematical foundation of the model. Okay, these distribution can be combined. Yeah, it can be combined by just add them up. Right? This is although it looks like, oh, what is the mixture of distribution? Like the name suggested, mixture means combine. When you combine distribution, you need to have certain probability, certain value. So the mixture of distribution is the combination of distribution with certain weight. Okay, for example, you can have like this multi-Bernoulli distribution to be denoted as the combination of the Bernoulli distribution. You have a multiple Bernoulli distribution combined with certain weight, then you get the multi-Bernoulli distribution. Okay. So these are examples of distributions that might arise in deep learning in representing the data. Okay. We will at least take into account of the Gaussian. We use Gaussian distribution and I think we use Gaussian distribution and the Bernoulli distribution in the derivation of the model, of like regression model using deep learning and classification model using deep learning. Now, I think almost the end, right? So when we work with machine learning, we are not actually just fitting data with the model and just that. We are actually relying on certain probability theory, and that theory is called the Base Theorem or the Base rules. In the Base rules, usually when you have a chance to observe event, and we call that the prior probability. For example, in population, there might be a chance of 1 in a million that you will get COVID, right? But the posterior probability, right? So if you see some person pass by, so there's 1 in a million that person get COVID. But suppose that you see that person, E is an evidence. You see that person not wearing mask, then the pH given E might increase to 1 in 1,000. Right? 1 in 1,000 that person might get COVID. Right? And this is called the posterior probability. Posterior probability is the probability of the event after you observing the evidence. And this come from the conditional probability equation. This is prior pop, and this is the likelihood that you observe E given H. Like E is like not wearing a mask and then get COVID. This is called the evidence. Sometimes you get this from the model. This is the priori pop that come from the evidence, that chance of wearing mask. Sometimes this is ignored. So Bayes rule, it comes from this. Because we know that P of A given B equal P of A intersect B divided by PB. And P of, that means P of A given B times PB would equal P of B given A times PA equal P of A intersect B. So that means if I were to move this P of A given B and then P of A, P of B given A divided by PB, I would have this Bayes rule derived from conditional probability. Okay, so these Bayes rules play important role, a crucial role in machine learning, because machine learning is this equation. Yeah, you will see that in the machine learning lecture, that the machine learning that we know is actually this equation. And when you train the model sequentially, when you train the model that is balanced, you need to multiply them with prior pop. Otherwise, you would have the biased model. Okay. So this is the Bayes rule. We will use it later on anyway to associating posterior pop with the model that it is trained, and also to derive the loss function in training the model. Right. Let's take and also I think just a few more slides. We will take a look at some important functions. First is sigmoid function, logistic function. Sigmoid function has a smooth transition, and it has a very nice property which we will talk about next time, that allow us to calculate gradient and optimize the deep learning model, the perceptron, by using mathematics in combination with coding. This is the logistic function or the sigmoid function. As x increase, the value transit from 0 to 1. Another function that is quite important is the soft plus function. The soft plus function here, the theta of x is log of 1 plus exp of x. This is a soft plus function. Soft plus have the value of 0 and then increase and become linear after it pass 0. This is soft plus function. Soft plus can be used to represent like the value that has that is like 0 or has the value of x when it's more than 0. And this can be, well, in deep learning there's a technique called the activation function called the ReLU, rectified linear. It can soft plus can replace that because this is differentiable. ReLU is not differentiable, right? So and this might arise later on, right? The soft plus. This is log of 1 plus exponential of x. Log of exponential is just that value, okay? That means when the value closer to 1, it will behave like log. When the value is a lot more than 1, it will behave like that value. When x is less than 0, then it has to be value of 0, so that it will be log 1, which is 0. Okay, so sigmoid and soft plus has certain relationship. That is, this is the sigmoid function. If we diff the sigmoid, we get sigmoid and 1 minus sigmoid, and we talk about it later on. And we take the if we diff the soft plus, we get the sigmoid. This is like the function is convertible from one to another. And what else? Take log of sigmoid, and you get the soft plus on the flip side. And if you integrate the sigmoid to a certain value, you get soft plus. And the soft plus minus soft plus reflecting out, you get value of x. So this is quite useful formula, useful properties. Although we will not use all of them, we will at least use the sigmoid and then see later on how it works in gradient derivation in the next lecture. Okay, now it comes to the last topics that we will cover tonight, which is I forgot to remove this out, which is information theory. Information theory refers to the learning that how events occur, and when events occur, there should be certain information that can be extracted, that can be learned. There should be certain variables that can be used to indicate that information. So it is the concept of learning that unlikely event occur might be informative than if the likely event occurs. So it gives us the information with different quality. Likely event give you low information, right? It gives you low information to predict the future because it happens every day. But less likely event will give you higher information,